Welcome everyone. In this video, we're going to talk about the firm's production technology, which is going to actually refer to the function that firms are using to take inputs to transform them into outputs. Therefore, this is the beginning of our discussion about producer theory. We've just now talked about consumer theory. Now we'll start thinking about the perspective from the firm. And here we're going to talk about the firm's production function, the firm's production technology, taking inputs and then producing outputs. And we'll see examples that are actually going to be really familiar to the utility functions we've seen. A lot of the same functional forms that we had for utility functions come back as production technology. As a matter of fact, the Cobb-Douglas production technology was originally formulated as a production technology. We've used it for utility. We'll also consider the technical rate of substitution and the marginal product. The technical rate of substitution, it's going to be kind of like the producer theory analog to the marginal rate of substitution from consumer theory. And the marginal product, kind of like the producer theory version of marginal utility. Kind of. Not kind of. And so what I'll say is there's a lot of similarities between consumer theory that come back with producer theory. This really helps us with a lot of actually some of the math. But the story is more complicated than just swapping out terms. Even so, it's worthwhile to pay attention for the direct similarities. One of the main sort of key direct similarities is between the consumer's expenditure minimization problem, which looks a lot like, is almost exactly identical to the firm's cost minimization problem. With a little bit more than today's lecture, you should actually be able to solve the firm's cost minimization problem, borrowing a lot of what we did from the consumer's expenditure minimization problem. Although, of course, we'll go over this a little bit more carefully. I'll have a lecture kind of devoted to cost minimization, but you've got kind of the foundation almost in place already, because there are such drastic similarities. All right, so when we're thinking about production, we have to pay attention to both the inputs and the outputs that firms are using. And so in addition to having like however many inputs are used as as part of the production process, and then however many outputs, typically we'll think of like 2 inputs and 1 output, we also have those prices, right? So we've got 3 prices we'll be thinking about: the price of the 2 inputs and then the price of the output, although we could have multiple inputs. You can also have multiple outputs. And so clearly we've got like these vectors we're going to be paying attention to. So the number of inputs and then their associated prices, the output, and then its associated price. By inputs, we mean like factors of production, typically like land, labor, and capital. For our purposes, it's pretty much going to be labor and capital. We're pretty much going to almost always restrict my consideration to situations where there's 2 inputs, and I'll almost always call them labor and capital, or I'll just call them input 1 and input 2. For capital, we mean things that are themselves inputs, themselves produced goods. So inputs to production that are themselves produced. So such things as buildings, machinery, computers. And in a more complicated class, we would think of depreciation being relevant. This basically would require us to invoke some type of dynamics, right? So we'd be thinking about dynamic programming or some type of dynamics that we need to be considering. We won't do that here. It's worth realizing that this is definitely a possibility. So thinking about how you'd solve dynamic programming problems and sort of a dynamic, by dynamic I mean, suppose we're thinking about several periods into the future. So now we've got a time dimension. So then over time, your stock of capital might depreciate. We could do that. We're not going to. We're just going to focus on a single time period, sort of a cross section. And the reason why is because we want to sort of master the basic tools, and that's actually kind of enough complication for us already. Often the inputs will be measured in flow units, so we'll consider an amount of labor per week and amount of machine hours per week. And this is probably the last time I'm going to mention that. We'll typically, things would just kind of line up as we need them to, but that's sort of like a background question. All right, so whereas with consumer theory, we had limitations on what could be consumed based on like what was the consumer's budget, which would stretch as far as possible given the relative prices. Here, rather than having the budget set, we will have the firm's production set, which is going to be like the combinations of inputs and outputs that are going to be technologically feasible to produce. So you can think of all the collections of outputs you can get given the combinations of inputs you're using. You can think of the frontier of the maximal, like where you're employing all inputs. You can think of the maximal possible outputs you can get. And then you can think of all the combinations where we get less than the maximal amount of outputs, and that's how we get our entire feasible set, our entire production set of all the possibilities. So if we assume inputs are costly, though, we'll actually just focus on the maximal possible output given our inputs. Just like with budget, we focused on the budget line. We kind of ignored the rest of the budget set and just kind of focused on the budget line, except as regards changes in the budget set. Similarly here, we won't typically think about much more about the production set other than changes in how the production set could look. Typically, we're going to be just thinking about the boundary, the frontier. This is going to be defined by our production function. So that'd be sort of, here would be like a one input, one output, so we can draw this nicely. Our production set would be like all the combinations of the inputs and then the amount of output that we'd get. Well, here we just have like, one input. We could produce, if we maximally use our input, we produce along this line. That's kind of the idea. So the production set is bounded by our production function. Now in the two input case, we are going to describe our production relationships with an iso-quant. So remember, in consumer theory, we had indifference curves, and along an indifference curve, you had all the bundles that the consumer was indifferent between. For an iso-quant, we're thinking about all the possible combinations of inputs that are going to produce the same output, right? So we have, for a given iso-quant, iso, like what's constant? Well, it's the quantity. So for a given quantity, the iso-quant is going to give us all the combinations of inputs that produce that output, all the different ways to produce that output. So as I mentioned, there's the analogous conceptual object from consumer theory, but there's a really important difference. Indifference curves were labeled by utility levels, whereas iso-quants are labeled by production levels, by output. Well, consumers maximize utility. Firms don't necessarily maximize output. They're interested in maximizing profit. And so there's a little bit of a difference there. We're looking for like the highest possible indifference curve. We're not necessarily looking for the highest possible iso-quant. The other thing is, well, here we've got levels, right? With indifference curves, we only cared about the rank order of indifference curves. We only cared about the ordering of preferences, the ordering of ranking of bundles. The level itself, the magnitude, wasn't as useful. Didn't have a really good interpretation. Well, with production, clearly, like, the magnitude's going to matter because that's the amount of real goods you've got. All right, so here's a collection of the production technologies that we'll see, and they look really familiar. We have our Leontief fixed proportions, we have our perfect subs, we have our Cobb-Douglas. And then my note about notation. So the first thing is L is going to be the amount of labor input, K is going to be the amount of capital input. This is if labor and capital are entering as complements, right? Fixed proportions. The amount that we're going to be able to produce is limited, right? We're constrained by either the amount of machines available or the amount of labor available. Suppose A and B are both 1. That's telling me that I need 1 labor hour for every machine hour or whatever. And that's telling us that if I have extra machine capacity, but I run out of workers, now I'm not going to be producing as much. The amount of output I'm getting, F of LK is just representing the output, is going to be limited by whichever is smaller, A times L or B times K. So F of LK is going to be standing for, well, this is our production technology. It's a function over labor and capital. It's going to be the amount of output this thing's kicking out. Suppose labor and capital are substitutes, right? Then the amount I'm going to produce is going to be A times L plus B times K. And then reflecting the fact that labor and capital are indeed perfect subs, suppose A was 0. Now I'm getting all my production from machines. Or suppose B is 0. Now I'm getting all my production from labor. Cobb-Douglas, so this is relatively familiar. So it's going to be labor to the A power times capital to the B power. In consumer theory, we typically see this and we think of like whatever is this A set equal to 1. A is a scaling factor. It's referring to the scale of production, how much output if you use 1 unit of each input. Typically with consumer theory, this has been 1. With producer theory, this might be something other than 1. So typically in the exercises, in the IMX exercises I have, typically this is something bigger than 1. So Last thing is in terms of the notation. So by f of LK, this is just our production technology, and if we evaluate at a given level of labor and capital, that gives us a particular level of output. So I'll kind of use this interchangeably with Q. That's a little bit of an abusive notation, but it's kind of the same thing in terms of like the referring to the output that we're going to be producing. Varian likes using Y for output, and so we want to kind of pay attention to that as well. And some of the exercise, I'll think of Y, that's kind of hearkening back to Varian. So a word of warning, some authors will put K first. So you think of like the X argument and the Y argument, or like the X1 argument and the X2 argument. So I use labor first, then capital, which if we were graphing the function, labor would be on the horizontal, capital on the vertical. Some authors will do the opposite and put capital on the horizontal, labor on the vertical. That becomes relevant in kind of a couple places, but you just kind of want to pay attention if you're using a different text or whatever. All right, so we typically make some assumptions, just as we did with consumer theory. We make some assumptions with producer theory as well. We're going to assume preferences. We assume preferences were monotonic. We're going to assume technologies are monotonic. So with preferences, the monotonicity assumption was more is better. With production, our monotonicity assumption is going to be, well, when the amount of one input is increased, it should still be possible to produce as much as was available before. So that says if I have extra workers, I should be able to continue to produce more, at least as much as it should be at least possible to produce as much as there was before. That doesn't necessarily mean you will, right? But it means it's at least feasible. It should remain possible. It should not be impossible to produce as much as was feasible before. This is sometimes referred to as our free disposal assumption, and that is reasonable if getting rid of our extra inputs is costless. Then it's not inherently bad to have additional or have extras. The other assumption, just like with consumer theory, we assumed we had, or for well-behaved preferences, we assumed preferences were convex. So that was averages are preferred to extremes. Our technologies are convex assumption requires that if there's two ways to produce some particular output, their average should be at least able to produce at least the same amount. All right, so I want to introduce the terminology of marginal product. We mentioned already marginal product is a little bit like the analog from producer theory to marginal utility. So as I mentioned already, the levels kind of are important for producer theory in a way that's not true for consumer theory. So the difference with marginal utility and marginal product is, well, now with physical outputs, we no longer require that this is just an ordinal concept. Now the magnitudes are going to matter. In terms of actually calculating marginal products, well, our intuition from consumer theory holds. Marginal utility was just the partial derivative with respect to each good. Marginal product is going to be the derivative of the production technology with respect to each input. So here I've got the marginal product of factor 1. It's going to be the derivative of my production technology with respect to x1. My marginal product of factor 2 is the derivative of my production technology with respect to factor 2. So if I wanted MPL for the marginal product of labor, you take the derivative of the production technology with respect to labor. If I wanted MPK for the marginal product of capital, you take the derivative of the production technology with respect to capital. And the interpretation of marginal product is when I use one more unit of input, how much additional output am I getting? All right, so we can use these marginal products for something kind of immediately. We have the technical rate of substitution, which is going to give us the rate of trade-off between two inputs in production. So we had the marginal rate of substitution in consumer theory that gave us the trade-off between goods governed by the indifference curves for a consumer, right? The rate at which a consumer is willing to trade off one good for another while remaining indifferent. The technical rate of substitution gives us the trade-off between inputs to produce the same level of output. So this is going to be the slope. This is going to be a derivative. It's going to be like the slope of the isoquant, or it's going to be the negative of the ratio of the marginal product of factor 1 to the marginal product of factor 2. Just like we had MRS was MU1 over MU2, TRS is going to be MP1 over MP2. And some authors will use, so this is technical rate of substitution. Some authors will use marginal technical rate of substitution, or marginal rate of technical substitution, or rate of technical substitution. And by this, all we mean is the ratio of marginal products. So whereas MRS is the ratio of marginal utilities, TRS is the ratio of marginal products. We typically make the assumption of diminishing marginal product. So this is the assumption that the marginal product of a factor is increasing as the amount of that factor increases. As you use more of a particular output, if you use more of a particular input, the amount of additional output you're getting is going to be smaller than the previous unit. This is typically reflecting some type of bottleneck, like if we keep adding workers but we run out of machines for them, so machines become a limiting factor to increasing our productivity. That's kind of the idea. So that's my example. So suppose Paradise Bakery has 1 worker, 2 cookie machines. I don't know what a cookie machine is, but they've got 2 of them. The the diminishing marginal product assumption requires that the value in terms of additional output, additional cookies, from adding the second worker is going to be bigger than adding a third. And then the additional output achieved by adding the 4th and 5th is going to be still less, right? So think about how many additional cookies we're getting when we hire 1 more worker. And for each additional worker, the gain in terms of output is going to be smaller and smaller. Diminishing technical rate of substitution is we increase the amount of factor 1 while decreasing factor 2 to remain on the same isoquant. The TRS is going to go down, just like we had diminishing marginal rate of substitution. This is our assumption that's requiring isoquants being convex, kind of like our well-behaved indifference curves, right? That's all this is doing. We can talk a little bit about long run versus short run. So in the short run, there's some factors of production that are fixed, right? The definition of short run is just you've got some factor that's fixed. In the long run, all factors are variable, right? So this is kind of our reasoning. In the long run, you can change your factory space, you can retrain your workers, so on and so forth. And this is going to be relevant for some of the problems that we'll solve, especially like thinking in terms of profit maximization and cost minimization. So for those 2 problems, we'll have actually 2 varieties, the short run version and the long run version. And that'll be important to keep track of. Last thing I want to talk about is returns to scale. So we want to think about what happens if we increase all inputs. So this is captured by returns to scale. Constant returns to scale means that using twice as much of each input gives twice as much output. If we double the amount of each input, we get double the output. Decreasing returns to scale means using twice as much input less than doubles, gives us less than twice as much the output. Increasing returns to scale means if we use twice as much of each input, we'll get more than twice as much output. We'll get more than double the output. Mathematically, this is kind of what this looks like. We can take our production technology, we can scale up our amount of the input, and if multiplying each individual input is the same as multiplying the output, we have constant returns to scale. But if we multiply each input and the output that's generated is smaller than if we take t times the amount of output, then we have decreasing returns to scale. So you can think of t as like 2. So if we double the amount of inputs and then take f of, right? So we take those as inputs into our production technology and get less than doubling our production of fx1, fx2, then we have decreasing returns to scale. Here's how we check this. I don't know that I necessarily like this written out horizontally, but the basic idea is, all right, if we have a particular production technology, like this is Cobb-Douglas, x1 to the 1/2, x2 to the 1/2, let's carry through the math. Let's scale this up by t, this up by t. Well, what that requires us to do is insert a t under the square root in both cases. But then I can factor out the t, and I'll get t to the 1/2 plus 1/2. And then this right here is the original production technology. Oh, but wait a second. This is just t. That's this right here. And so this is showing that if I scale up each input by a factor t, we can manipulate this and make this look the same as, if I just were to scale up the output by a factor t. And you can think about what's relevant here is this exponent. Suppose this summed up to be greater than 1, that would give us more than t times the amount of output. Or suppose this summed up to be less than 1, that would give us less than t times the amount of output. And that would so t to the something greater than 1 would correspond to increasing returns to scale. T to the something smaller than 1 would correspond to decreasing returns to scale. Here we have t to the 1, right? 1/2 plus 1/2. And so we have constant returns to scale with this production technology. All right, so I'll go ahead and conclude here. Hope you enjoyed the video. See you next time.